Alright nerds, so we're back and we're going to keep going with our waves, well not waves so much as information systems, and today we're going to look at the electromagnetic spectrum, which are the types of waves which we get from the sun. And as I said, it's a spectrum, so it's a whole range, and that range is either in frequency and energy or wavelength, and we'll have a look at that in a minute. So our objectives today are to be able to identify the different types of EMS, as well as probably their wavelengths or wavelength ranges, be able to identify the various uses of different types of EMS, and to compare and contrast the advantages of microwave and radio wave electromagnetic spectrum. Alright, so the electromagnetic, basically what we're talking about is the energy we get from the sun. Now, this energy comes from all sorts of places, just that's the major source. But when we talk about using it, we're talking about energy that we're creating, usually via electricity, and we'll get to that in a little bit. Alright, so there are several different types, and they've got a range of properties that make them different. So they're all each suitable for different applications within communication systems. Now, we would use, just as a quick primer, we would use these as for communication systems because at times we're not going to be able to physically link our communication systems. Alright, so they include essentially like your visible light, which is this really tiny section here. That's what we can see with our eyes. Infrared, we sense this as heat. Microwaves and radio waves, which we can't detect. They're beyond our capabilities. Alright, so here's a good diagram of it, to be honest. We can see this is the wavelength in meters, so 10 to the 3. That's kilometers. Alright, and that's radio waves. Radio waves are anywhere between the hundreds of kilometers. Microwaves, smaller, centimeters, 10 to the minus 2. And infrared, we're talking about 10 to the minus 5. Visible is really small, and you'll see that there's protozoans here. Like, here's the size for roughly what they are. And if visible light is the size of protozoans, that's why we can see it, is because it's also the size of our eye cells. And because our eye cells are so small, but they're roughly the same range of the visible light waves. We've got ultraviolet, which is smaller, X-ray, and gamma radiation, or gamma rays, which are the smallest. Now, one thing you'll notice from before is that as the wavelength gets smaller, okay, the frequency gets higher. So as wavelength goes down, frequency goes up. Also, so does the energy. So temperature, like temperature is just a measure of energy. So that the higher this goes up, Kelvin is a different unit for it's absolute temperature, basically. So as it goes up, like this is if you heat something up to these temperatures, this is what that emits this type of radiation. As it goes up, so the energy goes up, the wavelength decreases. And here, this will be quite useful later on. We can see which ones will penetrate the Earth's atmosphere, and all these ones with yes, these are the ones we're able to say we can use for traveling out of space. The ones that won't penetrate for satellites communication, the ones that won't penetrate our atmosphere, we can't. Like, they just bounce off. They bounce off something called the ionosphere. UV light doesn't. That's a different thing. But over here we bounce off the ionosphere, and here we interact and get absorbed. But radio waves, radio telescopes are what we use to look out into space. And visible, we know visible light penetrates the Earth's atmosphere because we can measure it. We can see it. We can see stars at night. So this means that visible light gets through. Alright. So again, here's just another representation of the spectrum. And it just compares sort of a bit closer. So here's frequency and wavelength. That's the interesting part here. Here's the different types of radiation that links to that. But here you can see very clearly that as the wavelength increases, the frequency decreases. Alright, so these are the ones that we use in communication technologies. That's what we're talking about. Remember, we're talking about communication technologies. So in optical fibers, we use visible light. Okay, for remote control. Sorry, and this just means the remote control you have at your TV. We use infrared light, microwaves for satellites and mobile phones. Okay, TV broadcasting tends to be shortwave, and short to longer wave is our radio broadcasting. But you should probably get this table down. We need to be able to compare radio waves and microwaves. So microwaves are radio waves, but they're very, very short wavelength. So high energy, they're very high energy. Microwaves, they pass through the ionosphere. So we can use these for satellite. We can modify them to carry multiple signals, and that's the advantages of them. If we look at radio waves, the advantage is that they're actually reflected off the ionosphere. Now, the ionosphere is above the air that we breathe, and it's all plasma. So because these are because they bounce off, what they do is, so here's our Earth, and it's round. Because you can't send a straight line to the other side because the curve of the Earth gets in the way, we can use radio waves, and because they're reflected off the ionosphere, they will bounce around the Earth, and that makes them really useful. So they can carry messages over a very wide area, and they've got really simple aerials. This is a radio wave. This is a microwave. Basically, they're absorbed. Microwaves, the disadvantages are they're absorbed easily by water, and this is why, well, if you aim them at living tissue, as you've seen in a microwave, they cook it. So, and then they do need special aerials, again, these ones here, to detect them, to pick them up. So the disadvantage of radio waves is that they're limited. Because it's easy and limited, like the number of frequencies, so there's competition, and you actually can't just pump out radio waves to make your own radio station. You have to apply for a license, etc. So if we want to use both microwaves and if we want to compare them as well, both microwaves and radio waves, well, we'll look at the advantages first. And wires aren't needed. They travel through the air for both of them. So long distance travel and cheap travel. Like, there's no expensive cables being laid down. That's the advantage. The disadvantage for both is that they travel in a straight line. Now, this can be an advantage because it's predictable, but it means that we need repeater stations. Okay, so to go around things or through over mountains, etc. We'll need repeater stations. Alright, so let's have a quick look at a parabolic antenna, and it looks like this. Okay, so it's this shape, and it's that shape for a reason. So basically, any rays, all the rays that come in case you haven't picked up on it yet, all the electromagnetic spectrum, it's all light. Now, it's not light that we can see, but it's still light. So it travels the same way light does. So light comes in straight, and then bang, bounces off, but it's parabolic, which means it's not even a simple curve, but it is a concave mirror that bounces all of them into a focal point. Now, it's actually a bit more complicated than that. They bounce it into a focal point up the top, okay, and then that has another reflector which pushes them all down to it's called a feed horn, but essentially, yeah, it's the microphone, or well, it's not a microphone, but the detector that picks it up and turns it into an electrical signal that can be used. So that's how the antenna work. The transmitters, so that's a receiver. A transmitter is pretty much the same, looks exactly the same, except it works in reverse. So it pumps the signal out onto the reflector, which then hits the parabolic mirror, and it shoots it straight out. Alright, so that's the electromagnetic spectrum.